Welcome students. In today's lecture, we shall discuss regarding effect of source inductance in a single phase full converter. Right. So in the previous class, you have read about single phase full wave rectifier or full converter with R type of load and RL type of load. But we have considered an ideal case where there is no source inductance or source resistance. That means the derivations or the average voltage which you have obtained, that is for the ideal case where we have not considered source inductance or source resistance. But in general, there will be the presence of source impedance. Right. So there is a presence of source impedance. So when there is source impedance is there, if I assume the impedance is of resistive type. So if resistance is there, then there will be some drop with respect to the resistance which you have considered. So accordingly, there will be some reduction in the output voltage. But if you consider another scenario where your source has inductance, if you assume the source has pure inductance, so how does the switches or how does the operation will be affected because of the presence of source inductance, right? So if you observe this circuit diagram, this is the normal circuit diagram when you have considered single phase full converter with RL type of load. Okay, but now we are considering how the circuit will operate if you consider source inductance. So the circuit will be modified like this. So assuming my circuit has some inductance, or source has some inductance in place, that inductance is called as LS, source inductance. So you have already seen the operation of circuit with respect to single phase full wave converter with RL type of load. But now let us see how the switches will be operated, the SCRs will be conducting, or the circuit will operate under the consideration of source inductance. Okay, the same circuit I have redrawn as an equivalent circuit. Okay, so let us discuss step by step. So if the terminal 1 is positive, if the terminal 1 of source is positive, then current I1 flows, okay, and that current I1 will trigger, or when the triggering pulse is given at omega t equal to alpha, thyristor T1 and T2 will be conducting. Similar case which you have considered in the full wave rectifier. Okay. Similarly, when terminal 2 is positive, then the thyristors T3 and T4 will be conducting whenever you provide the gate pulse, or whenever you trigger the thyristors. T3 and T4 will be conducting. Right. So this is the equivalent circuit. So whenever my source, the same thing, I have considered terminal 1 and 2. So during the positive half cycle it is V1, and during the negative half cycle it is V2. So two different, that means I can say VAB and VBE. Okay. So when terminal of V1 is positive, then the current flows through V1. So from inductor, thyristor T1, thyristor T2, load. Okay, and when terminal V2 is positive, that means this terminal 2 is positive, then the current flows through inductor LS. This one is inductor LS. Current T3, thyristor T3, T4, load. That means when this one is, or during the positive of the supply voltage, or when this polarity or this terminal is positive, then the current is flowing from Ls, T1, T2 and load. Similarly, in this case it is from V2, Ls, T3, T4 and load. But what makes the difference? Because of the existence of Ls. Okay, so I have shown when V1 is positive or when terminal 1 is positive, the current flowing through it is I1, and when terminal 2 is positive, the current flowing through it is I2. Obviously it is load current, but I have given the naming as I1 and I2. So when you are considering the ideal operation of single phase full converter with R and RL type of load, the situation which you have considered is whenever T1 and T2 are conducting at omega T equal to pi, T1 and T2 will be reverse biased, and obviously T1 and T2 will be turned off and T3 and T4 will be into the on state, comes into the on state. That means T1 and T2 are the outgoing thyristors. I am talking about turn off at this instant at omega T equal to pi. Or else you can consider here also. If you consider omega T equal to 0, what are the outgoing thyristors? Outgoing means which are going to be turned off. So T3 and T4 will be turned off. And incoming thyristors are, incoming means which are going to be conducting when you provide firing, when you trigger the thyristor. So T1 and T2 will be conducting. So when T1 and T2 will be conducting, so outgoing thyristors and incoming thyristors, we assumed that the transition or the current transition or current flow will shift from outgoing thyristors to incoming thyristors instantaneously, and that means T3 to T4 to T1 to T2, the shift in current will take place instantaneously. But if you consider this Ls, source inductance, which does not allow sudden changes in current, or there will be a gradual increase in current and gradual decrease in current. It doesn't happen instantaneously. So, the same operation we shall discuss now. How this source inductance is affecting the performance. So, I have drawn I1. I1 is when terminal 1 is positive. I2 is when terminal 2 is positive. Okay. So what happens is, this one is the firing angle alpha. This duration is firing angle alpha. Okay. So at omega T equal to alpha, T1 and T2 are triggered, and what happens? The current starts flowing through T1, load, T2, as I already told. Right? But one more assumption here is the load inductance is very high, so that my current will be always continuous. Right? So I may assume it's as a straight line. My current is continuous. I am not considering the discontinuous mode of operation, I am considering the continuous mode of operation. Current is continuous. So what happens is, right? What happens is, when T1 and T2 are conducting, are conducting, the current in T1 and T2 slowly starts increasing from 0 to, this one is I0. This one is I0. So it starts increasing from initial value to I0. That means it doesn't increase immediately because of presence of inductance. When T1 and T2 starts conducting, the current gradually increases from 0 to I0. Actually, this is omega T equal to alpha. So this duration is alpha. So this is how the current rises, and then it will reach us to I0. Right? Similarly, at the same instance, T3 and T4 should automatically turn off, but because of the source inductance, the same criteria follows here. The current will not become zero instantaneously. or the thyristors T3 and T4 will not be turned off instantaneously. It will take some time. So I2 is corresponding to outgoing thyristors. Okay. So now what will happen is at omega t equal to alpha. So if I consider this one is I naught. So alpha to this duration, the current will decrease. So I can say this value is I1, increasing from 0 to I naught. This is regarding T1 and T2. This is regarding T1 and T2. So what about T3 and T4? Their current is decreasing from I naught to 0. So this from this duration to this duration, T3 and T4 current I2 is decreasing. Right? So what you observe from this is at omega t equal to alpha you have triggered thyristor T1 and T2, but the current slowly increases. At the same time T3 and T4 do not turn off immediately, the current gradually decreases. So this is nothing but I2. So if I combine this I1 and I2 as the output voltage or current, so what will be your waveform is, so this one is I1, right? So I1 will be, if I say this one is my I naught. Okay, so what is happening? This is increasing like this, I1. Okay, it is reaching I naught. At the same time, this is decreasing. This is regarding I1. This is I1, and this one is I2. Right? So I am combining this I1 and I2 here. So from omega t equal to alpha to some angle mu. So I can say this angle is mu. What is mu here? It's called as overlap angle. What is the overlap angle is, if you observe properly, I1 is increasing from 0 to I naught, and I2 is decreasing from I naught to 0, outgoing thyristors. So in the duration of mu, thyristors T1, T2, T3 and T4 are conducting at the same time. That particular duration is called as overlap angle. So mu is called as overlap angle. So in this duration, thyristors that are conducting are thyristors that are conducting are T1, T2, T3 and T4 are conducting. Right? So when these four are conducting, what will happen? The entire circuit is short circuited. So there will be no output voltage. Right? T1, T2, T3 and T4 are conducting. Right? And this value is, and this point is, I can say it is alpha plus mu. Alpha is the firing angle, mu is the overlap angle, and up to alpha plus mu, it is the thyristor T1, T3, T4 and T5 will be conducting in this overlap angle. Okay, so if you consider this to the next cycle, what happens? So it is I1 is increasing, and again it will start decreasing here. And what will increase now? I2 will increase. So this is how it will come. So I can say this one is I2 and this one is I1. Right? So I2 is like this. So still if I continue, this one will decrease again, and here it will increase. So and it continues like this. So again if I combine this, so at this point this is decreasing and again increasing. Here which one is increasing here? At omega t equal to alpha, pi plus alpha. This one is pi plus alpha. This point is pi plus alpha. Which one is increasing? Here it will be I2 will increase, I1 will decrease. Okay, that means when T3 and T4 are the incoming thyristors, T1 and T2 will be outgoing thyristors. That means which are going to be turned off. So the current will decrease and current will increase and the cycle continues. So if I complete here also, again decreases and then here it will be increasing. Right. So this is I1, I2 and a combination of that. So this one is I1 and this one is I2. Fine. So as I said, when T1, T2, T3 and T4 are conducting, this leg and this leg is short circuited. So the output voltage V0 will be equal to 0. So let us draw the output voltage waveforms during this period. Right. So prior to mu, during alpha, T3 and T4 are still conducting. So T3 and T4 are still conducting. So my output voltage will be like this. Right. And during overlap angle, output voltage is 0. So this one, T3 and T4 are conducting. This is overlap angle. I can say you can trace this voltage. So during this angle, T3 and T4 are conducting. From mu, during mu, there is no output voltage. And then T1 and T2 starts conducting. This is my output voltage. Again, here it is. Again, T1 and T2 continue to conduct. There is no output voltage as T1, T2, T3, T4 continues to conduct. Short circuit, output voltage is 0. And again, T3, T4 will conduct. And this is the output voltage. And again, it continues. So the same voltage I will draw it here as the output voltage. Fine. So what did you observe from this is, because of the existence of source inductance, we are observing 4 thyristors are conducting at the same instance. That particular period is called as overlap period, the time is called as overlap period, and the angle corresponding to it is called as overlap angle. So in that duration the output voltage is 0. So what is the effect that is being created by the source inductance? First one is the mean output voltage will be reduced. Right? The output voltage will be reduced. That means effects by this particular source inductance. The mean output voltage will be reduced, and also the current and the voltage waveforms will be distorted, and the performance parameters will be affected. I repeat, because of this, the mean output voltage will be reduced, and the second one is the current and the voltage waveforms will be distorted, and the third one is the performance parameters will be affected, or it will be altered, it will be modified. Right? So this is the overview or the explanation regarding the effect of source inductance in a single phase full converter. Right? So according with this, we need to compute or calculate the average voltage. We have computed average voltage without considering LS, but now you need to find out average voltage or the output voltage V0 when LS is present. That analysis we will discuss in the next class.
Welcome students. To continue with the previous topic, we have discussed regarding the effect of source inductance and full wave converter. Let us proceed with the analysis part. So this diagram you have already seen. This is the equivalent circuit of full wave converter by considering the load inductance LS. Okay, so we have the points A, B, C, D. Okay, let us try to apply KVL to the loop A, B, C, D and A. So applying KVL to the loop A, B, C, D and A. So what is the equation you will get? V1 minus Ls into di1 by dt, LDI by dt. So here I am writing it as I1 with respect to I1 and Ls. So Ls into di1 by dt, that will be equal to V2 minus Ls into di2 by dt. Fine. So and what will be V1 minus V2? V1 minus V2 will be equal to Ls into di1 by dt minus di2 by dt. Okay, and you know that V1 will be equal to Vm sin omega t. That means I can say this V1 is VAB, right? V2 will be equal to minus Vm sin omega t, and this is VBA. Okay, substitute these two values V1 and V2 in this equation. So what is the answer you will get? It will be 2Vm sin omega t equal to Ls into di1 by dt minus di2 by dt. Number this equation as 1. Fine. And the next step is we have assumed load current as constant. So here the load current is constant. Okay, so as I already told, this I1 and I2, this I1 which is flowing in the when T1 and T2 are conducting, this I1 and this I2 is nothing but the output voltage I0. So I will write I1 plus I2 will be equal to I0, right? So if I differentiate this, I will get di1 by dt plus di2 by dt will be equal to 0, right? So number this equation as 2. Okay, now you have now you have equation 1. So how can you write equation 1 in terms of di1 and di2 is di1 by di2 di1 by dt minus di2 by dt will be equal to 2Vm by Ls into sine omega t. Number this equation as 3, right? And you have di1 by dt plus di2 by dt that equal to 0. If you add these two, what you will get? You will get 2 di1 by dt, that will be equal to 2Vm by Ls into sine omega t. So final answer will be for this is di1 by dt will be equal to Vm by Ls into sine omega t, right? Number this equation as 4. Number this equation as 4. Fine. So let us move on to the next step. Okay, load current I1 through thyristor pair T1 comma T2. That means I1 is corresponding to thyristor T1 and T2. Builds up from, as when I'm discussing the concept, I told that the current will incoming thyristors current will starts increasing from 0, right? So it will T1 and T2 builds up from I1 through T1 and T2 builds up from 0 to I1. That will be is equal to I0. Okay, so don't get confused. This I1 is the instantaneous value of current, and this I1 is the average value, which is nothing but equal to I0. Okay, I0 during overlap angle. During overlap angle mu. I have already discussed what is the overlap angle mu. So that is at omega t equal to alpha. What is our I1? Obviously it is I1 equal to 0, because at omega t equal to alpha it is starts building up from I1 equal to 0 to till it reaches to alpha plus mu, right? So and at omega t equal to alpha plus mu, my I1 will be equal to I0. That means when T1 and T2 are conducting, my current I1 is starting to increase from 0 to I0. At alpha it is 0, and at plus alpha plus mu it is approaching the I0 value, which I have shown in the waveforms. Like it is increasing like this and it is approaching the I0. So now we are discussing this point. This one is 0 and this one is I0. So this is the duration, and this is 0 is at alpha and this point is at alpha plus mu. Okay, so and we know that already we have derived di1 by dt will be equal to Vm by Ls into sine omega t, right? Let us integrate on both sides. So it is increasing from 0 to I0. I1 is increasing from which value to which one? Which value? It is increasing from 0 to I0. So the limits are from 0 to I0, right? So as I'm integrating with respect to dt, so what is the value I will get? It is di. That will be equal to Vm by Ls integral alpha by omega, and it is alpha plus mu by omega, and here it is sine omega t dt, right? And the time duration which you are considering it from alpha to alpha plus mu, right? So what will be the answer for this? It will be I0 will be equal to, so if you integrate and if you substitute the values, you will get I0 will be equal to Vm by Ls minus cos omega t, and what are the limits? Alpha by omega and alpha plus mu by omega. Fine. To proceed further, let us continue this derivation for this. So that will be equal to Vm by Ls into minus cos alpha plus mu by omega plus cos alpha by omega. That will be equal to Vm by omega Ls cos alpha minus cos alpha plus mu, right? It is nothing but I0. So number this equation as 5, right? So V naught is 0 from alpha to alpha plus mu. As I already discussed, you have the overlap angle where T1 and T3 and T4 are the outgoing thyristors and T1 and T2 are the incoming thyristors. So in this overlap angle mu, when these thyristors T1, T2, T3 and T4 are conducting, I told that your output voltage will be equal to 0, right? So that is the reason V naught is 0 from alpha to mu. So let us, for that, what is the average output voltage VOX? Actually V naught is the average output voltage, but in this duration we have V naught is 0. So by considering that part also, let us find out the average output voltage VOX, which is given by VOX is equal to Vm by pi. Again 1 by pi in fact. Okay, 1 by pi Vm sin omega t. I have taken Vm outside. So it is alpha plus mu to alpha plus pi sin omega t d omega t, right? So average output voltage from which point you are considering? It is from alpha plus mu to alpha plus pi. Please try to understand. Okay, because from alpha plus mu you are considering, but not during mu. Okay, that is the reason. From alpha plus mu to alpha plus pi you would be having output voltage. If you go back and see your output voltage waveforms, you have the negative half, then there will be no output voltage during the overlap angle, and then you have the output voltage like this. So this point is nothing but alpha plus mu, and this point is alpha plus pi, this point. Okay, alpha plus pi in the sense this value also, this one. Okay, this point is nothing but pi plus alpha. That is what we are writing as alpha plus pi. Okay, so sin omega t d omega t. Let us do the integration for this, and we will proceed further. Right now it is Vm by pi minus cos omega t alpha plus mu to alpha plus pi. So that will be equal to Vm by pi minus cos alpha plus pi plus cos alpha plus mu, right? I have applied the limits. Now it will be Vm by pi cos alpha plus mu minus cos alpha plus pi. Yeah, I have rewritten the equation. Now this alpha plus pi, so I can write it as cos alpha cos pi minus sin alpha sin pi, sorry, sin pi, right? So what will be the answer you will get for this? It you will get minus cos alpha, right? Why? It is cos alpha and cos 180 is minus 1, and sin alpha and sin 180 is 0. So this one is minus 1. So answer you will get is minus cos alpha, right? So the equation will be Vox equal to Vm by pi cos alpha plus mu plus cos alpha. That means I have substituted this value here, this one, right? Okay, but without considering this ls in this condition, So what is the average value of the output voltage within the case of full converter? Average value of output voltage at no load is given as V naught equal to 2 Vm by pi cos alpha. Fine. So maximum mean output voltage VOM will occur at what value? Alpha should be equal to 0. Okay, so the maximum value will occur at 2 Vm by pi. Okay, okay. Now, so VOM equal to 2 Vm by pi. So what will be my Vm? It will be VOM by 2. Okay, so now therefore VOX can be expressed as VOX, this equation VOX, I can write in the place of VOM, VM, what I can write? In the place of VM, what I can write is, I can write VOM by 2 into cos alpha plus cos alpha plus mu, right? And also we know that in the previous derivation steps we have seen I naught is equal to Vm by omega ls cos omega ls cos alpha minus cos alpha plus mu. Already you got this value. So what will be the value for cos alpha plus mu from this? Cos alpha plus mu from this is cos alpha minus omega ls by Vm into I naught, right? So let us substitute this value in this equation. So what we will get? VOX will be equal to right. So we need to substitute the value of cos alpha plus mu in this equation VOX. So what will the answer you will get? Vm by pi into cos alpha plus cos alpha plus mu. This is the equation, already you have it. So from that Vm by pi cos alpha plus cos alpha minus omega ls. I am substituting this value. Okay, omega ls by Vm into I naught. Okay, so that will be equal to Vm by pi 2 cos alpha minus omega ls by Vm into I naught. Okay, so that will be equal to 2 Vm by pi cos alpha minus Vm omega ls by Vm into I naught. So VOX will be equal to 2 Vm by pi cos alpha minus this one is cancelled, this will be 2 pi f into ls by pi into I naught. That's simplification, that's it. Okay, so Vox will be equal to 2 Vm by pi cos alpha minus 2 f ls by ls into I naught. Okay, so this is the average output voltage in the case of, if you consider uh, the condition of effect of source inductance. Okay, so with this we are done with the single phase effect of source inductance in the case of single phase full converter and its mathematical analysis. If you go back and see what are the derivations we have done, so let us see what are the derivations we have done. So we have obtained the equation for I naught. Okay, we have obtained the equation for Vox, that is the case of effect of source inductance. Okay, thank you.